So in this video, we're going to look at integration by substitution. And so the idea behind integration by substitution is that we are trying to undo a derivative that was formed by using the chain rule. So we're trying to get back to the original function. But when you use the chain rule, you take a complicated function and then you multiply it by a derivative of some inside piece of it. So you create a more complex function when you take the derivative. And so what we're going to try to do is undo that to identify the portion of the function, which is the derivative, and then work backward to get that simpler but still composite function that we would have started with. So we're going to look at a couple of different examples of what integration by substitution problems can tend to look like, and then work backwards to try to do the substitution, simplify the problem, do the antiderivative, and then reconstruct our original problem. Now, there are two sort of ways that you tend to notice problems that can be done by integration by substitution. And one of them is sort of this classical way where you have a function with an inside piece and then next to it is its derivative. And those in some ways are actually easier to spot because they are really clear in that there is a complex composite function in the problem. And if you look at the inside of that, the thing that's sitting next to it is the derivative of that inside piece. So all the pieces are already there. But you can also have a situation where substitution would be appropriate, where you have a function multiplied by its own derivative. And this is really a special case, but it shows up frequently enough in problems that we're going to treat it sort of as its separate scenario. So an example of this first scenario where we just have a function and its derivative would be an example like sine x cosine x. Cosine x is the derivative of sine x, but this is an example where we can apply substitution. In the second scenario, we would have something more like this example where we have e to the x cubed, and then the derivative of the x cubed is the 3x squared. Another example would be this example where we have sine of x squared plus 2. The derivative of x squared plus 2 is 2x. And so we have the components there for both the sort of larger function and the derivative of the inside sitting there next to it. So let's look at this first scenario where we have sine x cosine x. Now, in this case, the function that we want to call u is going to be the function itself, not its derivative. Now, in a sine x cosine x scenario, we could let either one be the derivative, but so that we don't have to deal with the sign change. When you take the derivative of cosine, you get minus sine. So we don't have to deal with the sign change, S-I-G-N change. We're going to let u be the sine function, and then cosine is its derivative without a sign change. So we're going to let u be sine x. Then we take the derivative of both sides of this in differential form. So u becomes du, and then sine x becomes cosine x times dx. And then we make our substitution. So this portion of the expression only to the dx, that cosine x dx gets replaced with du right here. And then the sine x itself gets replaced with just the u. And now u du is just essentially a power rule. Raise the power by 1, divide by the new power, add c, and then you replace the u with the original substitution that you made. So u squared becomes sine squared x. And we end up, again, it's a very simple case that it sometimes seems like it's a special case, but it's really just a simpler version of, essentially this was raised to a power, but it happened to be power 2. And so when you take the derivative of it, the powers go away, and it seems like it was never really a composite function at all, but in fact it is. Now, in our second case, we have a composite function and the derivative of the inside right next to it. So this would be an example of our 3x squared e to the x cubed. Now, whenever you have an exponential function, the inside is the exponent. So we're going to let the inside be our u substitution. U is x cubed. Taking the derivative of that, u becomes du, and x cubed becomes 3x squared dx. Sometimes, particularly when you're just getting started, it may be helpful to rearrange things so that pieces that go together are next to each other. So the 3x squared dx is together, and then your e function is separate from it. It's not sitting in the middle like it was originally. Then you make your substitutions. X cubed in the exponent up here becomes e to the u, and then the 3x squared dx collectively gets replaced with du. And then it's easy to integrate from here. E to the u, the antiderivative of that is e to the u plus c, and then we just put u back. And so you can see you had a more complex function, and you get a simpler function. It's still composite, but it is simpler than it was because it's no longer a product. And it's also very clear that if you take the derivative of this, you will, in fact, get 3x squared e to the x cubed. Now, if we look at the second example, this sine function, this is very similar. We're going to let u be the inside of the sine function because that derivative, I take the derivative to get du, the derivative of this is 2x. So again, I'm rearranging 2x dx is going to be replaced with my du right here. And then sine of u gets replaced here. And the minus sign is still there. And that's useful for us in this particular problem because the antiderivative of sine is minus cosine. The derivative of sine is positive cosine, but the antiderivative changes the sign because the derivative of cosine is minus sine. So the antiderivative of sine is minus cosine. And that means the minus sign cancels out. We end up with cosine u plus c, and then we put the u back. You can never stop when you still have a u in the equation. You always have to go back to the original variable that you started with. Now, as examples go, these are pretty straightforward, but I wanted to also include some tips for choosing u. And so I put together another list of a couple different problems that we can think about in terms of how do I know what to choose to be u and what not to choose to be u. So in a problem like this, where I have tangent of x times log of cosine x, the log of cosine x is a more complicated function than just tangent of x alone. So even if you don't know that the derivative of log cosine x is minus tangent, this is a better guess. If substitution is going to work, this is more complicated. And therefore, if it's going to work, then that has to be your substitution. Typically, logs also tend to be things that you want to make u substitutions for, because we can't integrate log as it is. There's no basic log rule for the antiderivative of log x. So it's very useful to make replacements for log functions. If they will yield to substitution, let that be u, and then see if you can obtain something similar to the rest of the function after you take the derivative. So again, more complicated function, logs, those tend to be good u functions. Now, in this particular second example, we have log x over x. Again, logs tend to make good substitutions. And you'll notice that the derivative of log x is 1 over x. So this is essentially like that case 1 example. It's the log x function times its derivative, because we could rewrite this as log x times 1 over x. So that is that case 1 function. Same thing basically in this third problem. You have a log with a different base, but it basically, the derivative is slightly different, but it basically works in the same way. You've got a log someplace in the problem, and importantly, you have another multiple of the variable sitting out here in the denominator. Again, logs make great u-substitutions because we can't integrate them as is. And so if there's a log in the problem, if substitution is going to work, that's a good way to make u. And it turns out that when you learn integration by parts, logs make good u functions anyway. So if you've got a log, think about it as the u. D is another example that is actually similar to the second example. It's similar to that simple case that we did at the top. The derivative of arc cosine is -1 over the square root of 1 minus x squared. So this is another example of a function times its derivative, essentially. Now it's a constant multiple of its derivative, but that is another example of that same type of problem. Now, typically, if you have trig functions involved in the problem, you want to think about the angle inside the trig function as being your possible substitution. Cosine of x squared plus 2 times 2x. Again, the cosine of something is the more complicated function. So it's that inside piece that will get substituted. Same thing for sine of e to the x plus 1. The derivative of e to the x is e to the x. This is inside the trig function, so it's that inside part that gets substituted. If you have an exponential function, as we noted in our example earlier, it's the exponent that is considered the inside piece. And so substituting for that exponent is the thing to try. So if we have something complicated like secant squared x e to the tangent x is our substitution. The derivative of that is secant squared x. If you have polynomials, particularly ones that are raised to powers, it's the larger polynomial, inside the power, that is typically your substitution. If you've got roots, think about whether or not the thing under the root is going to be your substitution. Now, if you're doing a change of variable problem, then this won't work. In a change of variable problem, the derivative of the underneath the radical won't be equal to this. But if it's going to yield to substitution, then it's the thing under the radical. When you take the derivative, it has to equal or be a constant multiple of the thing on the outside. Now, if you have denominators, rational expressions, then it's often useful to look at the denominator as the thing that you want to make your substitution for. In this example, the derivative of 1 minus z squared is -2z. So it is a constant multiple of the numerator. And so that is the suggestion here, is to make the denominator the substitution. Same thing for a problem like B. The derivative of the denominator is 2x minus 2. And when you do the antiderivative, you'll get a log of the denominator as your answer, but this is how you identify what to do. Again, this isn't always going to work. Sometimes you will have to apply other techniques, do other substitutions before you can find the correct way to integrate this. But if your denominator is t to the 4th plus 1 and your numerator is t cubed, the derivative of the denominator is 4t cubed. So it is a multiple of the denominator. And that is where you want to make your substitution. Same thing for even trig functions. You don't necessarily want to use the power, because powers tend to generate chain rules, which tend to be complicated. But just think about if you've got something in the denominator here, this just take the trig function. Same thing if you have like t to the 4th plus 1 to the 5th power, you would just take the inside component there. Just take cotangent to be your derivative. And yes, the derivative is negative cosecant squared of x. Again, constant multiple of the derivative that you need. That is the correct way to identify the substitution. And then again, same thing for this one. The derivative of e to the x plus 3 is e to the x. So the denominator is what you want to use for your substitution. Now, sometimes you will have problems where it may seem like if you make a logical substitution that you will have to make a string of two substitutions. So for instance, in this example, if I were to make a substitution for x to the 2/3, the derivative of x to the 2/3 is a multiple of x to the minus 2/3. I could do that and rewrite the problem like this, right here. But the problem with that is I can't integrate this as it is. I would have to make a second substitution where I let tangent be equal to another variable. I can't use u again because I've already used it. So I pick w. And then the derivative of tangent is secant squared. And that then reduces to something that I can't actually integrate. It's just a power rule now. But then when I go back, I will have to resubstitute back to get back to x again. I will have to do that twice. Because just going back to w won't be, staying in w isn't good. Going back to u is not going back all the way to the original problem. I have to go back to x. On the other hand, though, if I'm thinking about this carefully, I can choose the substitution that involves both the tangent and the x to the 2/3. Because when I take the derivative of that, I will have a chain rule, but I will get everything I need. I will get the secant squared, x to the 2/3, and I will get the x to the minus 1/3, all in one substitution. And then I will be able to essentially integrate. I will basically get to this point, but just with a u and not with two layers of substitution. So if it can be done in one step, it's easier to pick a slightly more complex substitution and do it in one step, taking advantage of the chain rule, accounting for some of the problem, rather than doing it in two stages. Now, if you feel like it's easier for you to do it in two stages, then by all means, my recommendation would then be to do it in two stages. It will take longer, but if that's going to help you get to the correct answer, then that's what you should do. But when you get comfortable with it, making this more complex substitution and doing it in one step will make the problem go faster. Now, another important thing to keep in mind is that your derivative can never end up in the denominator. So that's one thing that if you're trying to make a substitution and you're trying to locate the chain rule portion of your derivative and you're trying to put it in the denominator, you can't integrate like that. So that is a hard no-no. It simply isn't going to work. No chain rules work that way. They all have to be in the numerator. They all have to multiply. In fact, if you have a rational function where your derivative is it looks like it's in the denominator and not the numerator, then probably that's a clue that your numerator is a higher degree than the denominator, and you need to do long division first. Now, a couple of examples we looked at earlier, we looked at examples where the coefficients and everything matched perfectly. And like the derivative of e to the x cubed, the derivative of x cubed was 3x squared. That was already in our expression. But what if we had x squared e to the x cubed and we didn't have the 3? Or maybe we had a different coefficient. What would we do then? In those circumstances, constant multiples we can account for. We can simply substitute in additional coefficients to make things match up or cancel out as we need them to. So there's a couple of different techniques that we can use for this. But let's look at our example here, e to the 3x. This is a very sort of basic kind of technical substitution, but it only ends up involving constants that have to be manipulated. So we don't have a formula for e to the 3x per se. We have e to the x. And so we make a substitution. U is 3x, and then du is 3dx. And I don't have a 3 here. So one way to do this, and this is typically the way I deal with it, is I divide the 3 out, and I put it on the other side of the equation as a 1/3. And then I replace what I have in the problem. So I replace dx with 1/3 du, and then e to the 3x with e to the u. And then I get the 1/3 there, the way I need it. Now, another strategy is to substitute into the problem the number that you need times its reciprocal. The number you need times its reciprocal is 1. So 1/3 times 3 is 1. You're not changing the problem in any way. But then what you're doing is you're essentially multiplying here by 1, and then the 1/3, you don't really need it to do the antiderivative, so you just kind of leave it there. And then you substitute, you had du was 3 dx, and so you substitute du for 3 dx. So that constant has been repaired, and then you just make the substitution, and the 1/3 is there because you multiplied the problem by essentially 1. And so that 3 gets absorbed and disappears, and you're leaving the 1/3 behind. Either method gets you the same answer, so they both work perfectly well. Use whichever one works best for you. Again, I tend to use the first method by just moving the constant over to match up what I have in the problem. But either of those methods are perfectly correct. This typically tends to come up in a lot of the first stage of problems in a substitution problem set. Typically will have the coefficients there that you need. And then as soon as you get about 5 or 6 problems in, then they'll start changing the coefficients on you, and you'll start needing this example. Another example would be, again, this rational function. We said that the denominator is the best guess for your u substitution. The derivative you get is 2x minus 2, which is not what is here, but this is 2 times the expression that you need in the numerator. So you can factor out the 2 and move the 2 to the other side so that you get 1/2 du will replace the x minus 1 dx, x minus 1 and the dx. The numerator and the differential portion. And then you're just left with, as your coefficient, your extra half. Du over u is what you end up with. And then you end up with log of u plus c. And then you put your u back. Now, there are some problems that are substitution problems, but are in disguise because somebody has done some simplification. And that is typically an example like this, where the derivative of e is e, right? E to the x, the derivative of it is e to the x. And here normally we'd say, okay, there's an e in the denominator. We make the denominator our derivative. Oh, but there's no e in the numerator. So the way that we fix this is we multiply by 1. If you have an e to the x in the denominator, multiply by e to the minus x over e to the minus x. If you have an e to the minus x in the denominator, then multiply by e to the x over e to the x. Now, if the e to the x is in the numerator, you don't need to do any of this. You can just pull the denominator out as a multiplier, a constant fraction, and then just do the integration. So this only applies if the exponential is in the denominator, but not in the numerator. Now, in this problem, we're going to multiply by e to the negative x over e to the negative x. And when we do that, e to the negative x is going to make this a 1. E to the x times e to the negative x cancels out. That's 1. And then I'm going to be left with 3e to the negative x. And now the derivative of this denominator is going to be some constant multiple of e to the negative x. And that's what I have in the numerator. So now I can actually do my substitution with my denominator. And then I have to repair my fraction because I have a 3 here and not the 2. And when I make my substitution, I can pull the 2 out and then make my substitution. That's going to get me another 1/3. So now I have 2/3 out front. And then my denominator becomes u and my numerator becomes that 1/3 du. And then I can integrate, I get a log. And then finally I put my u back in. Now, again, sometimes problems can get more complicated. Sometimes these are going to require additional techniques. So in this example, substitution can get quite complicated, and sometimes it can be used in combination with other problems. In this example, what we end up with is the derivative is actually not in the numerator. The derivative we need is x minus 3, and we have x minus 4. But what we can do is we can split up the problem. This one we can do by substitution. This one we would actually have to do by completing the square and doing actually a power rule. So for instance, this one is a substitution. We let u be the denominator, x minus 3. The derivative is 2x minus 6. So that's twice what is up here. So that's our 1/2. And then this one, when we actually unfoil it, we factor it, and we get x minus 3 squared, then we apply the power rule. You can think of this as doing a separate substitution. It's just a linear constant, so it doesn't really, the derivative of x minus 3 is just dx. So it doesn't really produce any operations, but here we can think of it as technically doing a second substitution. But in the end, what you have to end up with back at x. So this first expression becomes, and I dropped the half here. Oh, and I did that on purpose. You have a 1/2 log of this plus 1 over this. And it turns out this is a perfect square. So if you bring this inside take the square root of a perfect square, then you just get log of x minus 3. Now, some problems, particularly when we're involving trig functions, you can actually apply your substitution in 2 different ways. This occasionally happens when you have odd powers of sine and cosine. They're both odd powers. Or if you have, in this case, even powers of secant combined with an odd power of tangent. So in this problem, if I take a substitution, u is equal to the tangent, then du is secant squared. I can replace the other secant squared with 1 plus tangent squared, and I can end up with basically a polynomial expression based on tangent, and then I can integrate it, and my answer eventually is in the form of tangents. But I don't have to do that, because I can take out a secant tangent as my derivative and then substitute in for secant. And then I will get an expression that is in terms entirely of secants. Now, I can always make substitutions. Even powers of tangents can be replaced with even powers of secants. And these expressions are algebraically equivalent to each other. They're both perfectly valid, and they are both algebraically equivalent, give or take a constant. These trig functions in particular are where you sometimes will see plus and minus one differences between the two functions. But if you were to make your Pythagorean identity substitution, but these problems can happen, and they're both perfectly valid ways of approaching these problems. Again, the even powers of secant with an odd power of tangent can do this. And if you have combinations of odd powers of sine and cosine, you can also substitute either for the sine or the cosine, and you will get equivalent expressions. Okay, we've seen a lot of different examples of substitution in this discussion. And so hopefully that will make it a little bit easier to identify what to make your substitution for, and then how to proceed. And the important thing to keep in mind is you cannot force this. If you make a substitution and you take the derivative and you don't get a constant multiple of the other part of your function, of your integral, you can't proceed. You can't force it. You have to be able to make a clean substitution so that everything converts to u. You can't integrate if there's still some x's left in the problem. It's maybe you're just using the wrong technique. Maybe you chose the wrong substitution, but you can't integrate if you have combinations of u and x. You have to be able to swap them all out cleanly. And when you get to the end, you can't stop when you get to the antiderivative with your u function. You have to go all the way back to your original variable. And that means if you have a complicated problem where you make multiple substitutions, then you have to go back all the way to the original variable. And that may mean making multiple substitutions in reverse. Happy integrating.